Hello, good day. So it's been a while that we have studied certain interesting simulations regarding an industrial machinery, supposed to be an induced draft fan impulse, radial impulse. And we had discussed about the kind of simulations that is generally adopted by the industry experts in order to design, develop, and produce these heavy engineering structures. So today we are going to see yet another interesting structure, which is a structural simulation, a structural engineering product. And it's a industrial structure, and this industrial structure is modeled using a three-dimensional CAD system, and we have designed it with members, which is you know, available standards on the standards, and we have designed it for a specific purpose. So these industrial structures are generally designed based on certain requirements. It could be either used as a shelter for any of these machineries, and this could be used as uh, a shelter uh, for you know, keeping structures. I mean, keeping products. I mean, different kinds of materials, raw materials. So like we generally call it as a godown or a warehouse. Okay, so those kind of structures are generally designed using steel structures, steel members. So members like tubes, angles, beams, channels, etc. And then with suitable gusset plates and bracings, etc. And these structures are designed based on the principles of structural mechanics. So today, here we are seeing typical industrial structure, okay, that is going to accommodate a certain set of machineries. Okay, and we are using uh, beams, ISMB. So ISMB beams. Then we have angles. We have tubes, tubular sections, and we also have plates. So we can see that this is an I section. I section that's put on the plate. Okay, and you find some 16 to 20 dia bolt holes, and these are the cross members, and these cross members are designed with the plates, the bevel plates. Okay, and this is the bracing, cross bracings. Now these members are all designed for a certain purpose, for taking different kinds of loadings, transferring loads from the top member to the bottom member, and likewise transferring uh, seismic loads to the other structures nearby. So these are all the bracing members, the tubular elements. So this is the I section, and then we have a tie beam, and then on the roof we have the plates. Okay, so this is all about the structure, and this is made using some CAD tools. So now what we do is we are going to focus now onto the simulation part. So we know that the members are all steel, and the steel has got a certain material property. So based on which the initial loading conditions are taken. So we are considering two design phases. The first design phase, we don't have any plate members. The roof is completely detached, removed, and then the simulation is performed on the skeletal structure. Okay, now we are applying a certain load, a remote load to the structure, and we are applying a certain force on the members. So these are all the tubular members, and on the tube we are applying a certain load, and that loads are applied remotely. So from a certain height, there is a load which is getting equally distributed on all the members. And then we have the constraint mechanisms, how it is constrained. So we have given spring support to all the members, assuming that it is kept on soft soil, and it completely embedded into the soil. The foundation is within the soil. The base plate or the gusset plate is welded and firmly into the foundation, the pedestal. Okay, and the structure is anchor bolted to the pedestal. So this is the assumption. So having performed the simulation, we find that there is a certain amount of deflection on the structure. So this is almost about 10 mm. So 10 mm is the maximum load or the deflection. Okay, the maximum deflection because of the load on the top. So it is nothing but the roof weight, complete roof weight. Okay, on the structure. What is the deflection? Okay, now we also find what are the stresses. So you find the stress value as about 12 Newton per mm square. So 12 Newton per mm square is considerably a low value, and now we also find that the deflection is about 10 mm, which is a very big value. So usually 10 mm deflection and all cannot be compromised. So we try to find out like, what exactly could be the reason that there is a lot of deflection. So these are the loads are applied directly onto the members, the tubular members, and whatever load is applied, it is applied directly onto the members that is good in taking bending loads, bending stresses. So which means these are all members which is extremely good in taking stress value, the bending stress value. Now what about the deflections? That is very important. Now since the deflection value is 10, this structure cannot be further processed, which means we need to seriously do something on the design so that the deflection value reduces, okay, by at least say 80% or say 90%. Okay, so now what we do is, let's see like what would be the other simulation processes. So we have performed a normal mode fundamental sorry, frequency simulation. So we find this is the normal mode. So this is how the possible ways of vibration or the possible ways of structural deformations. So this is the second way. This is the third way. Okay, so these are the frequencies. So the first frequency is about 1.79, almost 1.8 hertz. The second is about 2 hertz. The third is about 2.4 hertz. So now we find that the displacement values are all considerably lesser. So the first fundamental frequency we find it is about 0.9. The second fundamental frequency we find it's again 0.9. The third fundamental frequency is 0.9. It's within 0.9 with a second decimal variation. So now let's get into the third stage of operating frequency. The structure is subjected to constraining mechanisms and other boundary conditions. And then let's try to find out like what are all the frequencies, the force frequency, the operating frequency. So exactly when the structure is constrained and then the external boundary conditions like the loadings are applied, these are all the ways, the possible mode shapes of the structure. So here it's 1.3 hertz, then the second is about 2.6, then 3.9, then we have 4.0, 4, 4, 4. So there are three values, see 3, 4 values, which is in the range of 4 and 4.5. So these are all the possible ways that the structure can vibrate. Okay. So let's see the ninth, 8th, 9th and 10th. We see like these are all the ways. Okay. The model shapes of the structure. And now once we have done with the force frequency simulation, we will get into the transient simulation, a time dependent simulation. What will happen when there is a time bound load which is applied onto the structure? How is it going to bother or how is it going to matter with the stability of the structure? So for that we are performing a dynamic transient simulation where we are giving a certain time function. So we give some time functions. So the time functions are half sine based with an amplitude of 1, a start time of 0, and then it's prolonging for 0.1 seconds, zero point 0.1 seconds. Okay. Then the second time function, we say it is 0.15 and then it is for a period of again 0.1. So there are 3 time functions given, and once the time functions are given, we have to give a excitation. So that is usually the base excitation. We call it as base excitation because this kind of loads are all of a sudden, we call serendipity, or we call, like all of a sudden forces or loadings. An earthquake can be an all of a sudden force, that is a seismic load, and a wind load. A wind load, a sudden hurricane, okay, a cyclone, all can be time dependent. It's based on certain time. So now we are giving a base excitation to the regions. So these two ends are fixed and the other end two regions. Both the end regions are all fixed and the in-between regions are all supported on certain spring, which means there is a soft foundation. Okay, and once the excitations are given in terms of uh, impulse. So here one excitation is a displacement. Displacement is applied in terms of amplitude. And then the other one is again a displacement, and then we are giving an amplitude. So we can specify whether it's a displacement or whether it's a acceleration. So whatever kind of loadings we can give, that will be applied for that particular quantum of time. Okay, in the form of a half sine impulse. Okay, so here let us say like the excitation type is an acceleration, and then I am giving an acceleration in terms of g value, and I say that there is a 6g kind of loading that I am giving to the structure. And similarly, here there is a displacement value. So now, how does it affect? Okay, so yeah, so the displacement. Okay, so now, yeah, this is a transient system. Okay, and so there are three different functions that I have defined. So let me give some displacement only, and so this displacement, this is acceleration. and I'm giving that to this, and let's give uh, displacement something here, and then we okay. So now let's give it as an acceleration, and we perform the simulation. So once we give the acceleration, that is going to get uh, acted on the structure for that time function whatever we have given. So here we find there is a deformation. So this is how the structure is going to deform. So yeah, so this is the way the structure is going to deform for the acceleration what I have given. Okay, and this is going to cause a deformation of 154 millimeters. So about 15 centimeters of a deflection. That's a huge deflection. And that is because we are giving a G value. So G value is high here. It is almost how much? Uh, so the G value here is 6G. 6 times the acceleration due to gravity is a loading. Okay, so now let's see what is the stress value. So this is how the structural response is going to be. This is the way the structure is going to stress. We have 436 Newton per mm square, and we know that the yield stress is lesser than that. So the structure can possibly collapse. Okay, so now let's try to find out what is how the deformation looks. So these are the regions where the structure is fixed. Now let's see like what is the deformation on the top. So we will find that this is the response. So the deformation response, and let's see what is the stress value. So this is how the stress values are, and then let's see how the acceleration is. This is how the acceleration comes. So it will excite to the maximum, then it will dampen down. So it will dampen and it will go to zero because we are giving a model damping factor. Okay, so this is how the structures can uh, respond. So these are all the different areas. Let's say now let's take the top portion, the top members, the side members, the bracings. So we have the bracings here. So these bracings, yeah. So these are all the cross bracings, and on cross bracings, how does it behave? So these are all the values. This is how the responses are, the displacements are. So now let's average it, and this is how the average is going to look like. Okay. Now let's try to give the excitation in terms of uh, displacement. So now let's say the structure is going to get loaded based on a certain excitation. So this excitation is in the form of displacement, and then how the displacement is going to act on the structure for a period of time. Okay, so that is given in terms of amplitudes. Yeah, so now it's done with its yes. So this is how the structure is going to behave. So this is how the structure is going to behave respond. Yeah, yes. Okay, so this is the initial jerk. Okay, and then over a period of time, that's going to increase the deformation. So this is almost about 330 mm. Okay, now let's see how the stress values are going to happen. I mean, yes. So this is how the structure is going to, these are the regions where the stresses are going to affect. Yeah. So you can find that, we can find how the structure is going to bend. The tools are bending here. Okay. So now what we do is, let's try to find out like what are all the, yeah, so this is the displacement. Okay, and now let's see how the stress values are going to be. We'll find the acceleration, is the peak acceleration. Okay, and the velocity. Yes, so let's try to change it back to acceleration, and then let's see how it's going to behave with the time function. So the g value, g values can also be changed. So now it is 6g, we can make it 3g. Okay. Now, if the structure is supposed to be subjected to about 8g or 10g, okay, then we need to redesign the structure. So there should be a lot of additional members added so that the deformations and stresses are neutralized. The extreme values are all neutralized. Okay, so this is it. And then now we focus on the random vibration part. Okay, so we assume that the structure is going to randomly vibrate. That is for a certain value of, so we are defining a power spectral density. Yeah, so this is how we are giving a harmonic load, and the harmonic load is given with an amplitude of 1. Okay, and then we are giving a excitation, a base excitation, acceleration due to gravity, and so it's about 6.5 g value, and then I'm giving a remote load on the top. So the remote load is like this much, 8,000 newtons, 2,000 newtons the sideways, and then we perform a simulation. So this is how the deformation looks like. So very small time period, and for that time period, this vibration is going to be uh, applied onto the structure. So we are able to find that for a very small duration, that power spectral density. So it's the shock wave, it's the shock loading, it's a kind of shock loading which is applied onto the structure, and you find that this particular region, okay, there is a huge response that is coming on the structure. Yes. So this particular region, there is a response. And let's try to find out like what are the responses. So now let's see what is the displacement at this point. So this is how the displacement looks like. Okay, and then the bracing, this particular point. Okay, so this is how it looks. So this is the cross bracing. And now every member on the top and bottom is also going to experience the impulse, the responses. Okay, so all these members are all subjected to responses. And here again we have the response patterns. Okay, so now this is a response Okay, displacement versus frequency. Frequency versus displacement. Now we can also find out what is the stress. Okay, so now this is the one mass stress with respect to the power spectral density. This is the frequency. Okay, now we know that the frequency variation. So 4 is that particular region in that value what we saw. There were 4 different frequencies in 4. So 4, 4.0, 4.1, 4.3, 4.5. So there were 4 different frequencies with 4 hertz, and that is what is being highlighted here. So this is the peak harmonic. So this is the place where there is going to be a peak harmonic or a response on the structure. Okay, so otherwise, otherwise when there is the load which is acting stagnated, there is no issue with the structure. But then the same load with some impulse, okay, can definitely damage the structure. So that is what we mean by this particular graph. Okay, so now what we do is we get into the second design mode. So in the second design study, what we have done is we have braced the whole structure. We have filled it up with plates. So which means there is a roof which is bolted onto the rooftop, the structure. And now the situation is going to be something like this. Okay, for which there is a structural simulation performed, and we will find that once the structure is roofed, so we find that yeah, this is how the structure is going to deform. Okay, so this is going to have about 5.6, 5.7 mm deflection. Now let's see what are the stress values. The stress is about 10 point, 11 point something. So structurally, this is stable. Okay, the deflections are very less. The structure is stable. So now what we do is we try to find out the fundamental frequencies. And the first fundamental frequency, we have 4.6, then we have 4.7, then we have 4.8 and 5.5. So these are the 4 different fundamental frequencies. So what we do now is we will get into the forced vibrations, the forced frequency. So here we'll find that it starts from 1.5 hertz, 4.25 hertz. So 4.25 hertz, it's again uniformly distributed. Then 5.4, 5.5, 5.96, all the other frequencies are all influencing the other members. The first three values, the first 3 modes, the 1.5 hertz, 4.2 and 5.4 hertz, these 3 hertz are influencing the complete structure. Okay, whereas the other modes are all influencing the members, the support members. Now let's see. The transient part. This is the operating frequency part or the force vibration part. And let's set up a transient simulation and try to find out. This is the way the transient simulation on the structure. So for a certain duration of time, there is a load which is applied on the structure, and that sudden structure or an impulsive load when applied onto the structure. Okay, this is how the structure is getting deformed. So it's the sudden jerk or a impulse on the structure. Okay, so the displacement is enormous, 254 mm. So it's about 25 centimeters. It's a very big value. Now this is how the structure is going to get stressed. So you can see that every member is getting distorted. And then here we find the volumetric stress is about 118. Not 118, it is in fact 1186, which is almost about some 4 or 5 times than the yield stress of the material, the base material, steel. Okay, so let's find out, like for this particular function. Okay, now let's see the displacement factors. Yeah, this is how the displacement is. It looks like, okay, at that point. So now let's take this point and let's take the roof. Okay, and now let's try to take this I section. Yeah, so now this member. Okay, so these are all the members which was highly uh, responsive. Yeah, so these three members were highly responsive. Okay, so that is what we see here. So all the peaks, the responses in a very short duration. Okay, so now let's see what is the stress values. So this is how the structure is getting stressed. Okay, so now let's see how it is getting stressed at this point here. It is very high. The responses are very high. Okay, that is what we saw in the animation, that this cross bracings, what you see here on this left side, that particular region was subjected to huge responses, impulse. Okay, now let's see what is the acceleration. So this is the acceleration for that particular member. Now for this member, this is how the acceleration is. Yeah, this is how it is getting accelerated. So now this member is going to be like this. So these are the peak responses, accelerations. Okay, now we have the velocity, the structure. So for each member you can find out. Okay, and now we can also find out the resultant of it. So yeah, so now this is with a time function. We are giving an impulse. Okay, and the time function is defined as a half sine wave, and then we have a base excitation, and the base excitation is in terms of acceleration due to gravity. So we are giving a 6g force, and to the 6g force, all three directions, x, y, and z. Where the initial portion we assumed that horizontally there is going to be some lateral loads which is given on the structure. Okay, because of earthquake. So now here we are trying to make it all the three directions. So which means that base excitations is caused three-dimensionally. It's a tremor. It's not because of one single movement. It's a huge kind of explosion. Okay, so now we are giving it in form of an impulse, and that's how we find. So we can also find out like what are the forces. We can also find out what are the forces. So the immovable joint is, this is how forces as time is going to act, f of t, and the immovable joints. So this is for this member, and for the end members. End members are all made immovable, and in between members, yeah, this is how the in between members it's going to act. So that's the force versus time. Okay, we can see that that force, it is going to dampen down completely. Okay, with respect to time. Okay, now yeah. So for all these members, we have found out this. So this is for the second member. For the third member, this is how it acts. The end members are all fixed. Okay, and that's why we get the graph like this. Whereas the interior members are all on the spring support. So there will be the influence of the loading that is going to act from the bottom. Okay, the excitation, the base excitation. Whereas the impact of that base excitation on the other immovable structures are going to be lesser. Okay, so now the end members are all immovable, fixed, and the inner members are all made to be on the spring support or on some sort of soil foundation. Okay, so with this, let me just conclude the session, and tomorrow let's focus on to some, not tomorrow, on the next episodes we'll be focusing on some blast simulation, blast inside a structure. a concrete structure or maybe a multi-story building. So how does it, you know, affect the structure? So that is supposed to be an explicit dynamics. So these are all transient implicit dynamics. These functions are all implicit functions. Okay, so the time dependent based on certain impulses. Okay, with respect to some excitations. These are all considered to be implicit functions. Okay, so now for a very short period of time, how that particular load is going to act. Now, the next simulations for the blast and for any kind of fluid structure interactions, we'll be dealing it as an explicit function. Okay, so that will be for a pretty long time. Okay, that duration has to be observed frame by frame by frame. We need to observe the patterns. I mean the simulation process. Okay, so we'll come with the blast simulation in the next episode, and today whatever we have done on a civil structure or a structural engineering part, okay, this is going to be a very interesting session for the structural engineers or for the civil engineers who are in the areas of designing structures, and it's very important equally to the geotechnical engineers also who are practicing foundation designs. Okay, so here there are, there is every part of a structure covered. All kinds of simulations needed or to be performed on the structure is covered here. Okay, so we have the structural simulation, we have the structural superposition, then we have done the model simulations, and then we have done a model superposition also. We have done a force frequency simulation, we have done a direct transient simulation, and we have also performed a direct random vibration simulation. Okay, so now based on this, there is a lot of changes which can be done onto the structure by introducing several cross members. Okay, and there is a possibility of reducing the thickness of the structure, the roof structure, and by introducing a lot of other members which can safely transmit the load, the remote load or the direct loads acting on the structure safely into the ground, and similarly vice versa, the kind of excitations from the foundation to the structure. Okay, so let me conclude by saying that please subscribe to this particular channel, and you will be able to see and get yourself introduced to very interesting simulations, practical and logical, how it can be practiced. Okay, so also kindly share it with other engineers so that they also get an opportunity and they also get a benefit out of this. Okay, so thank you very much for your most valuable support.